Okay, this is the video lesson for 3.6 Rational Functions Day 2. And on this first part, it's just going to kind of be a recap of end behavior. And remember, end behavior was either a horizontal asymptote or a slant asymptote, and as we saw, even a parabolic asymptote. Okay, so first off, remember we have y equals 0 if the degree of the numerator is less than the degree of the denominator. All right, then we had y equals k, where k was not equal to 0, and this is the ratio of the ratio of the leading coefficients. That's if the degrees are the same. Then we had a linear function, if a linear function with slope, we should say, and that is when we did long division or synthetic division, we would have an equation of a line. And in fact, you can do division every time and get one of these things. So like for instance, if I were to do long division on problem 2, I don't need to figure out, but if I were to do long division, it would be, you would get 3/7 as your answer. Sorry. Okay. You would get 3/7 as your answer. I'm not going to go through that, but this is definitely scenario B, and we would say that the asymptote is y equals 3/7. All right, now let's go back to number 1. What do you think about number 1? Okay, it is, we would have to do the division, but which one of these would it fall into? Definitely not A or B. It would have to be C or D. When I do the division, would I get a linear function or would I get a higher degree, like a parabolic? Okay. Now, I don't want you to get too caught up on the details, and you don't need to really do the division to see that if you were to divide here, you would have a linear. This would be scenario C. Okay, now probably it wouldn't just be y equals x. It would be y equals some number x or plus or minus some number, but y equals x would be the general form of the asymptote, which is really all that this is asking you. Okay, 3 looks totally out of left field, but really it's just that it's already been divided. Think about if you were to get a common denominator here, this would be a 4th degree polynomial then in the numerator, and when you divide a 4th degree by a 2nd degree, you get another 2nd degree. Think about your exponent rules. All right, and so this is scenario D. Really, this right here, though, is the, the quotient. X plus 3 is the remainder, which we would ignore, okay? So you would have a y equals x squared, or we can even say minus 2, but we're kind of moving more away from the specific, and we're moving more to the generic with some of these things. That's what you're going to use in calculus because it's more efficient. You don't want to actually have to do the division each time. We do the division in the beginning to make sure you understand why the answer is what it is. But now I think we're ready to kind of be a little bit more general, and that will create some efficiency. All right, but for now, let's just go ahead and sketch a rough graph. Rough graph doesn't mean chicken scratch. It means that it will not be specific to every point, will not be accurate, but you're still going to have your asymptotes, you're still going to have your intercepts. Those things are going to be the same. So I don't want you to get confused about rough graph and think that that means, it really means we've been doing rough graphs this whole time, okay, or rough sketches. All right, so first thing, are there any holes in this graph? Are there any terms that cancel? No. Okay, so let's move on to vertical asymptotes. Okay, x equals. Now, if you look at this denominator, I can see that x equals 5 is a vertical asymptote, and x equals -4 is another one. All right, horizontal or slant? Which one? Okay, so numerator's degree is higher than the denominator's degree. Numerator's degree is going to turn out to be cubic, or 3. All right, so this is where we can be a little bit easier on ourselves. The horizontal asymptote is probably not y equals x. It's probably y equals x plus or minus a number. But for efficiency, we can definitely let it be y equals x. I know that it's going to be a positive. It would be important that you would check here to see it's possible that it would be negative, okay? But we don't need to multiply everything out just to get my horizontal asymptote within a 1 or 2 vertical shift, because we're really just concerned about end behavior here. So we're losing a little bit of accuracy with the points, but our sketch as a whole is just fine, and we gain a lot of time when we do this, okay? I'm going to talk more about that in class, though. All right, so let's talk now about x-intercepts. All right, this is already factored, so we can see easily that we have a -3, 0 x-intercept and a 3, 0 x-intercept. And for this one, I am going to either underline it, put a star by it, do something, because this root has a multiplicity of 2. So the graph is not going to cross through that root. It's going to bounce off. It's going to be tangent at that point, which we already covered in our polynomials lesson. All right, y-intercept. Again, you don't have to multiply this out to find the y-intercept. Just plug in 0 where you have it. So we'd have 3 times -3 squared, which would be times 9. All right, that's going to give me 27. And if you plug in 0 here and here, you'd have -20. So we have -27 over 20. All right, so now let's go through and put all this stuff on the graph. All right. When you put your asymptotes on the graph, you definitely want to label them. Even if this is a rough graph, you don't want to lose accuracy when it comes to something like that. All right, so x equals 5. Label. X equals -4. You're going to label it. And then I have these points at -3, 0, at 3, 0, and then at -27/20, which is a little bit lower than -1. Okay, I didn't graph my horizontal asymptote. I want to show you something. I'm going to fill this in a minute, but I want to show you something. If all the horizontal asymptote is going to do is affect the end behavior and not the middle of the graph, but the end behavior, we could just might as well not even graph it in the middle. Now I am going to do that, but I want you to see if there really was supposed to be a plus or minus, and I believe on this one, if you really work it out, it's x minus 2. Notice that that will just bring that down to, it really won't make the end behavior look much different than it looks right now. Okay, so again, you're losing just a little bit of accuracy, but the general trends of the graph are all just fine. Okay, connect your dots. Now again, no big deal that you're crossing this asymptote in the middle. It's end behavior that we're concerned with. All right, from here, I have nowhere to go but up. Okay, oh, I'm sorry. Let me back that up. This was our multiplicity, our even multiplicity root. So it's not going to cross through. It's going to bounce down, and then here there's nowhere to go but down. All right, over here at -3, 0, just a regular root, going to cross through, and on this side, nowhere to go but up. Okay, now there's no other points on the outside, but these vertical asymptotes are just regular old singular vertical asymptotes, so they're going to split the behavior of the graph, and you're going to have these shapes. And a lot of times people call these parabolas, and that kind of bothers me because they're not parabolas, they're rationals. All right, let's move on to the next one. Okay, again, this is already factored, and again, nothing cancels, so there are no holes. So let's go ahead and find our vertical asymptotes. Here we're going to have one at x equals 0. We're going to have one at x equals -3. We're going to have one at x equals 4. And we finally get to one where we have an exponent on the term that gives us our vertical asymptotes. So do whatever you need to do to this. Circle it, star it. It only really matters if it's an even power, kind of like multiplicity. This is going to cause something different in the graph. Kind of already talked about it, but I'll go over it when we start graphing. All right, now, without multiplying out, what is the degree of the numerator? 3. Degree of the denominator? 4. So this is the nice case when I have a horizontal asymptote of y equals 0. Okay, x-intercept, let's look at the numerator. We've got one at 5, 0. We've got one at -2, 0. And again, multiplicity of 2. So circle it, underline it, star it, whatever. Both of these things are going to affect our graph differently than they normally would. Okay, y-intercept, plug 0 in for y, and you're just going to have to do the number crunching. Now, in this particular case, you plug 0 in for, I think I said 0 in for y, I meant 0 in for x. Plug 0 in for x, and you get undefined. Well, that makes sense because I have a vertical asymptote at x equals 0. So this is going to be a none. All right, let's go ahead and do the graph. Okay, so I have a vertical asymptote here, x equals 0, labeled it. I have one at x equals -3, and I have one at x equals 4, and I've already told you this is going to be a unique, a special vertical asymptote. If you want to circle it here or do something there, that is great. Whatever you need to do so that you don't forget what's going to happen. And don't forget your horizontal asymptote at y equals 0. Okay, I'm going to switch to go back to using a different color on the points because I think it makes it show up better. All right, I have a point at 5, 0. I have one at -2, 0, and there is no y-intercept. You can see clearly now why there's a vertical asymptote there. Okay, I really don't have enough information. All I know is that at -2, it's either going to go up on both sides or go down on both sides. So this might not be a bad place to start. Really though, you could plug any number you wanted in. Okay, so if you thought maybe plugging in a 1 was the easiest thing to plug in a 1. Now you got to do a little bit of number crunching. Honestly, I'm really only concerned if it's positive or negative. All right, but you actually get -1 when you plug in 1. I'm not going to spend a lot of time on the number crunching because you can do that on your own. All right, so this gives us another point. It's not going to allow me to connect anything, but I know that I've got to have something that looks like this. And it may go up from here, but it's not going to cross. And it's not because of that horizontal asymptote. It's because I know that there is no x-intercept right there. All right, now remember, let's go ahead and just attack this while we're thinking of it. X equals 4. Normally, the graph would have split behavior. But because x minus 4 is being squared, both the numbers a little bit before and a little bit after 4, they're going to have the same behavior. Okay? Imagine if I plugged in a 3.9 and a 4.1. They would do the exact same thing because I'm squaring, so the sign doesn't really matter there. Now, yeah, I got to cross through, and you might be tempted to kind of go back up here, but that would cause this not to be a function. What's really happening is it's just going to level out, and I kind of didn't leave myself enough room there, but it's got to level out. That's the end behavior. That's what that's all about. Okay, what about at x equals 0? Regular old vertical asymptote is going to split that graph. Now remember, this root at -2, 0 was an even multiplicity root, so it's not going to cross through. It's going to bounce off, come back up. It's like this is one big logic puzzle, okay? And you've got to figure out what's going to happen. Okay, opposite behavior, can't cross through because there's no x-intercept. And there we go. Now if you get a contradiction, meaning that you feel like your vertical asymptotes are causing you to not go through your x-intercepts or have an extra one, then you messed up somewhere, because these things will always work out. And when you're working on your own, you can definitely check it with a calculator. And this is a nice little technique as well if you feel like you don't have enough points. Okay, let's look at this next example. Okay, are there any holes? Nope. So let's look at vertical asymptote. We have one at x equals 1. We have another one at x equals 4. And they're just regular vertical asymptotes, so nothing to be concerned about there. In this particular case, the degree of the numerator is larger than the degree of the denominator. So my slant asymptote is going to be that y equals x. But because there's a negative right there, all right, it's going to be -x. And again, it probably isn't just -x when you do the division. It's probably -x plus or minus a number. But when we're talking about in behavior and numbers going out to infinity, it will be extremely insignificant. Okay? So this is good. You don't have to multiply it out. We're saving ourselves a huge step here, just to lose a slight bit of accuracy. And I know I harp on you guys about keeping accuracy, but keep in mind that we are just doing a rough sketch here. This is not entirely accurate, no matter which way you think about it. So if you're thinking about, well, how accurate does it need to be? Well, I'm giving you an example of what you need to do right here in the notes. What I'm doing in the notes is what I would expect you to do on the test. All right, 5, 0. We got lots of x-intercepts. That's good. That's going to make the graph easier to figure out. Plugging in 0 for x. That's going to give us, this is kind of a messy number, negative 15 halves after you simplify it. All right, so let's go ahead and sketch the graph. By the way, in case this just is really bugging you, when you do multiply it out, it does give you negative x minus 1, but I'm not even going to graph that, okay? But just in case you wanted to know. I know as a high school student, that would have bugged me. I would have wanted to do it and then check the answer with my teacher. So that'll satisfy all you guys. All right, so here we have x equals 1. Label it. X equals 4. Label that. Negative x. And again, this is truthfully not just negative x, but that's a good enough sketch. Because what's happening in the middle is not really the major concern for this asymptote. That's why. Okay, let's go ahead and put in all of our x-intercepts. None of these are doubles. I don't have to worry about multiplicities or anything. This is just your standard problem. And then my y-intercept is going to be, I didn't really leave myself a lot of room here, so I'm just going to go ahead and put it right there. Okay, that's really negative 7.5. All right, so start wherever you want, but keep in mind that you cannot cross over a vertical asymptote. So I'm going to connect these two, and that's going to tell me I'm going to keep going down towards x equals 1. And again, up here, this is going to affect the end behavior. All right, x equals 1 is going to split that graph. I don't have to worry about any bouncing off. This is just going to cross through, go towards the next vertical asymptote. Again, x equals 4, splitting the graph. And everything just works out perfectly. Okay, now the back is a little bit different type of problem. It's just basically taking all the skills that we've learned and putting them into a more generalized sense where we're not having numbers so much, but letters. So they tell us that A is less than 0 and B and C are greater than 0, but C is the greater of the numbers. Now this is going to play into when we graph. Put these things on the graph. Let's analyze what A, B, and C even are. It says f of x is discontinuous at A, B, and C. Now this could mean vertical asymptote or holes. Okay, let's write this down just because these are our notes. We don't know yet. Okay, y equals x is an end behavior for f of x. Now this is telling us about the degree. This is telling us that the degree of the numerator is 1 more than the degree of the denominator. All right, now the next three are going to really identify what our vertical asymptotes are. As x approaches A from the right, f of x is approaching infinity. That's a vertical asymptote. And on the other side of this vertical asymptote, f of x is approaching negative infinity. So this is basically telling us that we have a vertical asymptote, okay? And I'm going to go ahead and list this here, and it's at x equals a. And it is not a double vertical asymptote, meaning x minus a is not being squared or to a even power. Okay, because if it were, this infinity and this negative infinity would be the same. All right, look at 5. 5 is not a vertical asymptote. It's actually a horizontal asymptote. The reason is because this is talking about, I'm sorry. No, it's not. What is 5 talking about? I'm getting too ahead of myself. Again, as x is approaching a number, f of x is approaching a number. This is an actual point, but it's a discontinuous point. So this is a hole. All right, and so I'm going to go ahead and write this on part B. We have a hole at b, comma, 2. X value is b, y value is 2. All right, next thing, as x is approaching c, from both sides we get infinity and negative infinity. This is another vertical asymptote. So this is how you tell when you see that discontinuous, you don't know which one it is, they're going to have to give you more information. Now, I realize that on your paper, I can't remember if this is fixed, so if your paper says f of c, then you're going to write undefined, because it is a vertical asymptote. And if your paper says f of b, then you're going to write 2, because even though plugging in b gives you undefined, it gives you a point at 2. Now, I will clarify this in class just to make sure everybody's good on that. All right, what is the degree of the denominator? Well, I have 2 vertical asymptotes, and both of them are just singles because they are splitting the graph. Okay, so the degree of the denominator, oh, I'm sorry, I still also have the term for the hole. So I have the 2 vertical asymptotes and the hole. That's going to give me a degree of 3. The degree of the numerator has to be 1 more than that. It can't even be 2 more, because that would then give us not y equals x, but y equals x squared. And if it were any more than that, it would be cubic, and so on. All right. Now we're going to take all this information and we're going to put it on a graph. Now, we don't have numbers, but we do know that A is over here, and then B and C. Okay, I also know that there is a point at 2. All right, so let's think about this. A and C are vertical asymptotes. And we still need to go ahead and label x equals c, x equals a. And then I have a hole right there. I'm going to make it nice and big so that we can see it. Okay, we have y equals x as our end behavior. And so let's think about what else we know or what else could be. They didn't tell us anything about our x-intercepts, okay? So we don't have any other points. But what they did tell us was the behavior right around our vertical asymptotes. They said on the right side of A, the graph is going up, and on the left side of A, the graph is going down. Okay, so let me switch my color here, and I'm going to go ahead and put the hole in that color as well. So on the right side of A, the graph is going up, and on the left side of A, the graph is going down. Well, this fits into what you probably thought was going on there. Now, at some point, this has got to cross over and go through this hole. Now, in terms of going up or going down, again, they give us that information. On the right side of C, the graph is going up, and on the left side of C, the graph is going down. So, on the right side of C, we've got an up, and on the left side of C, we've got a down. Now, this is forcing an x-intercept on us, right? Which is fine. They didn't say we didn't have any. They just didn't say anything about it. All right, so when we're writing our equation, we've got f of x equals, now we've got to put x minus a, x minus b, and x minus c in the denominator. And you may be thinking, well, shouldn't this be x plus a? Even though a is a negative number, think about, that takes this into consideration. The term giving me that asymptote will be x plus a number, but if a is negative, what's minus a negative? Plus. So it takes care. You don't have to do anything special here. It's just, you know, what we would normally think it would be. All right, I know that I have x minus b in my numerator, okay, because of the hole, and I need the degree of this to be 4. So there's a couple of different options you have. we know that there's an x-intercept. Now I'm going to call this x-intercept k, so I'm going to make this be k. The easiest thing to do would just be to put this to the 3 power. Now this does take into account the crossing through, and it helps me get the numerator's degree to be 4. There are ways that you could still make this all work that are more complicated than this, but why make it more complicated than you need to? Okay, you're going to get to practice this on the assignment, and you'll probably have questions, so bring those questions to class.